Hello, in this video I am going to explain the real-time operating system based embedded system chapter 10 of Introduction to Embedded System Shibu KV. I recorded the concepts or topics 10.4 multiprocessing and multitasking and 10.5 task scheduling of chapter number 5 as a part 3 video. So first we'll try to understand what is multiprocessing and multitasking. So the multiprocessing means the ability to execute multiple processes simultaneously is referred as an multiprocessing, and multiprocessor means the multiple processes performing a multiple processes on the processor is called as the such processor is called as a multiprocessor. If any processor allows the execution of more than one process is called as a multiprocessor. And multiprogramming, the ability of the operating system to have multiple programs in memory which are ready for execution. So as you know, the process can acquire few states: ready, running, blocked. That is all explained in the previous video. So this is called as an ability of operating systems to have a multiple programs in a memory which are ready for execution is referred as a multiprogramming. And the question is, what is multitasking? It refers to the ability of the operating system to hold the multiple processes in a memory which the processor for executing one process to another process is called as multitasking. First, multiprocessing refers to the capability of or ability of the processor, and the multiprogramming and multitasking are ability of the operating system shows. So I repeat, multiprocessing is the ability of executing multiple processes simultaneously by the processor is called as a multiprocessing. And multiprogramming, the ability of the operating system to have multiple programs in a memory which are ready for execution is called as multiprogramming. Multitasking refers to the ability of an operating system to hold the multiple processes in memory and switch the processor from executing from one process to another process. So we have come across different words, what you can say, keywords in this context. There are the multitasking involves context switching, context saving, and context retrieval. The context switching means switching from executing the context from task to another task. For example, task 1, task 2, there are two tasks, right? They are executing. The task 1 is a priority 1 and task 2 is priority 2. So now at present the task 2 resumes with all the necessary peripherals what are required, resources required, only waiting for CPU, and CPU is allocated to task 2 and it is executing its task 2. And then when the task 1, which is a higher priority, which resumes with all the resources and only waiting for CPU, then the task 2 has to be suspended its execution and the CPU time is allotted to task 1. In such case, the text which is executed in task 1 has to be stopped, and the task 1 has to be stopped, and task 1 has to resume its execution of the text. So this is called as a context switching. Then context saving. What do you mean by it? But task 2 is a second priority, task 1 is a higher priority. When task 1 higher priority task resumes comes in a ready state, then task 2 has to give the CPU time to task 1. At that time, the already what it has executed half of its task, right? Maybe some intermediate results all are generated, so that we have to save it. This is called as context saving. Context retrieval. When the task 1, the higher priority, executes all its code and goes into blocked state, then task 2 with the lower priority will get a chance to execute its code, remaining code. Which one? The half of the executed already codes, what are the results generated, what we have saved, and that we have to again retrieve it back at the same positions, same status, and from then it has to execute. This is called the context retrieval. So it is explained better in this graph. So this y-axis process indicates, and this x-axis represents the time. So process 1 and process 2. So here the process 1 is running, then process 2, okay, initially, and when the process 2 come into ready execution, the context switch has to take place. This is, look at here, this is the space where the task process 1 or task 1 will give up the CPU time to task 2 to execute, because it's a higher priority process. So then while handovering, it has to save the context, save the current text in the the process 1, because it has not yet completed its execution. This is the remaining part of the code which has to be executed. So when the context switch takes place from process 1 to process 2, CPU time is allotted instead of process 1 to process 2. At that time, there is some small ideal amount of time it will take. It's ideal what they have shown. It is the time taken by the process 1 to save its context, okay, and then hand over the CPU to the process 2 to run its code. When process 2 completes its execution, complete code, at that time it handovers, means it give up the CPU. At that time, this ideal period is utilized for retrieving back whatever the data what we have stored for the process 2. Process 1's data what is already stored, it retrieved back and again start execution from the same point where it has left. In this case, I have pointed everything on the screen. So type of multitaskings. So nowadays you can see that embedded systems, for example mobile and all, are designed as a multitasking, right, devices. So then the question, then the importance arises, we have to program all the embedded or design embedded product with the multitasking operation. So then multitasking again classified into 3 types. Cooperative multitasking, and preemptive multitasking and non-preemptive multitasking. The question arises, what do you mean by cooperative multitasking? Cooperative multitasking, where the task or a process get a chance to execute only when currently executing task or process voluntarily relinquish the CPU. For example, task 1, there are task 1 and there is a task 2. So we have created, and task 1 is already hold the CPU time, and unless and until you complete its code execution and then give the CPU time to task 2, the unless and until the task 2 cannot execute. So voluntarily the task 1 has to give the CPU time to task 2. This is called as a cooperative. And here, since this type of implementation involves a mercy of tasks each other for getting the CPU time for execution. That's a mercy, means if that task 1 doesn't give up the uh, CPU time, task 2 has to wait for indefinite amount of time, means a longer period of time. So preemptive multitasking. In a preemptive multitasking type ensures that every task process get a chance to execute, and it may be based on the priority, it may be based on the amount of time it will take. So there are different versions of the preemptive task are there, so we'll discuss it later. So as the name indicates, the preemptive multitask, the current running task, for example, there are two tasks, task 1 and task 2. Currently task 1 is executing. The current running task or a process 1 and same. The task 1 currently which is executing is preempted to give the chance to the uh, task 2 to execute. The preemption of the task may be based on the what I told, time lost or priority of the tasks. If so, for suppose task 1 is lower priority, task 2 is a higher priority, then before when the execution starts with for that particular embedded system with the task 1 which is of lower priority, when the task 2 arises with a becomes ready to execute in a status, and then task 1 has to give up its CPU time to task 2. This is called a preemptive type. The task 2 will preempt the task 1. Non-preemptive multitasking, the process or a task which is currently given the CPU time is allowed to execute until it terminates. Terminates, completely go enter into blocked state, waiting for only IO. This is called as a non-preemptive type. The question arises, what is the difference between the cooperative and this non-preemptive? Even in cooperative also, the CPU, the task, unless and until willingly relinquish means willingly give the CPU time to the another task, unless and until it will hold the CPU time with it. So here also it is the same. So the process which currently give the CPU time is allowed to execute until it terminates, finishes its total completion, or it goes into block state, complete call. The cooperative and non-multitasking differ in their behavior when they are in the block state. In cooperative multitasking, the currently executing process did not relinquish the CPU, where in cooperative, when any task 1 is goes into blocked state, it may not relinquish, means give up the CPU time. It hold with that. When again it resumes back, it continue execution. But in this non-preemptive multitasking, when it is introduced into blocked state, then it give up the CPU time to the another task. So task scheduling. So in multitasking system, there should be some mechanism in place to share the CPU among the different tasks and to decide which process or a task is to be executed at a given point of time. So determining the which task or a process is to be executed at a given point of time is known as a task scheduling. So task scheduling policies, right, are nothing but an algorithms are there. For example, a shortest job first uh, means round robin, so first come first serve. So like that, a few algorithms are there. So that we have to adopt as a scheduler. So the same thing what is explained here. So kernel or a service applications which implements the scheduling algorithm is known as a scheduler. So what is the work of the scheduling policies? Preemptive, non-preemptive, cooperative policies what we have to adopt. So already I have discussed about all these three policies of the scheduler. So depending on the scheduling policies, the task acquire a different status: ready, running, blocked, so completed. The scheduler section. Thus, consider the what criteria for adopting the scheduling algorithm should be different in different embedded system. Sometimes if it is a CPU utilization, so efficient CPU utilization, if it is the criteria, main criteria in any embedded system design, then the scheduling algorithm should be always make the CPU utilization very high. So throughput. So if the maximum throughput is required, it should be always high for a very good embedded system or which one you are designing. That's why you have to choose the very good scheduler. Always it has to produce the high throughput. And what is the high throughput means? The number of processes executed per unit time, right? Turnaround time. So turnaround time is the amount of time taken by the processes for completing its execution. It's called as a turnaround time. Waiting time. This is the amount of time spent by the process in a ready queue, waiting to get the CPU time for its execution of the process code. Response time is the time elapsed between the submission of the process and the or creation of the process to the first response. It's called as a response time. And we'll see scheduling queues. There are three scheduling queues always. Job queue. The job queue contains all the processes in the system. And ready queue. The ready queue waiting for CPU time. The processes which are waiting for CPU time are in the ready queue. And then a device queue. The processes which are waiting for the IO devices is called as a device queue, waiting for IO devices. So you look at here, that is there are various queues you will get there. So this is the process job queue. When the processes get created, that listed in the job queue. When any of these processes which is get all the IO resources available, only waiting for CPU, we call it a ready queue. And the process already executed some piece of code and then pushed to the blocked state, then they enter into the device queue where, right, IO, it is waiting for IO resources. So this is how the scheduler will pick the processes from this ready queue, ready, and then the scheduler will schedule the IO devices, and then when the IOs which are used by this will made free and then allotted to these processes, and again these processes come into ready queue, and always the scheduler will pick the processes from the ready queue, and once the processes are get created, they are listed in the job queue. When they get all the resources only waiting for process for CPU time, then they listed, they enter into ready queue, they listed in the ready queue, and when they picked and executes the processor, and a resource request by the processors, if it is not available, then it can enter into device. When it is available, it enter again into ready queue and again picked by the scheduler, and it will execute it on the CPU. So all this, when it completely finish, the run processor to completion. So this is how the scheduler works, or the work of the scheduler. You can broadly view, have a look at this in this slide, so you will get a clear idea about this, and each and everything is explained. Preemptive scheduling. Preemptive scheduling in the sense, so preemptive means the based on the priority, or based on the time slot allotted to each task, based on the preemptive means you have to stop temporarily or the present task executing and give the CPU time to other. It's called a preemptive. The dictionary meaning stop temporarily. It doesn't mean that it is stopped permanently. Which one? The present executing task or process. It is stopped temporarily, and the CPU time is handed over to uh, the another task. It depends on which task, depends on the whether we had adopted which kind of policy or algorithm for the scheduler. If it is a round robin or a shortage job first or a preemptive type, okay, priority based. Every task in the ready queue get a chance to execute. Yes, it is the ready queue. Look at here, this is the ready queue, will get a chance to execute. When and how often each process get a chance, get the CPU time, is depend on the type of preemptive scheduling algorithm used in scheduling the process right here. So if it is a round robin, every process will be allotted equal amount of time. If it is a shortest job first, from ready queue, which process has the short period required for short period to execute, means which is a required very lowest time, that will be picked. If it is based on the priority, then the which process has the highest priority, that will be picked and executed on this, allocated the CPU time. The scheduler can preempt the current executing process and select another task from the ready queue for execution. The preempt a task, which task is picked a ready queue for execution. The current task is purely depend on the scheduling algorithm, that what I explained now. First, we'll just have a look at the I told you algorithm which I can adapt for scheduling a shortage job first, round robin and priority based. First we'll have a look at the shortage job. Shortage job first means in the ready queue. In the ready queue, so I already told, When the processes get created, it enters into job queue, and when the IO resources are available to it and only waiting for CPU, they are listed in ready queue, ready to execute. That's called ready queue. And the processes are picked, or a task are picked by the scheduler to allocate the CPU to execute their code based on the, sometimes it's a priority, based on the amount of time required to execute the process, which is the shortest. That's called the shortest job first, amount of, based on priority. Or sometimes it is the if it is a round robin, equals amount of time slot is allotted to all the processes, and which is created first or which is listed first, that is selected, right, and to the its next created task. First, that is called shortest job first. Shortest job first means the schedule algorithm sort the ready queue, the which is ready queue I just shown you, right. Sort the ready queues based on the process entered the ready queue, and checks whether the execution time of the new process or a short process is short than the remaining of the total estimated and currently executing process, and then it will arrange according to that. Sorry. If the execution time of the new process is less, the currently executing process is preempted and the new process is scheduled for execution. So with example, we'll try to understand. There is a problem is given here. We try to calculate here the waiting time for the processes and the turnaround time, how much time it will take to finish it off. The three processes of the for the process ID are P1, P2 and P3. Our estimated complete time is P1 required 10 seconds millisecond, P2 required 5 millisecond and P3 required 7 millisecond respectively. Enter into ready queue. As we have adopted to this scheduling algorithm, the shortest job first. The first, the P2 is picked because it has the lower priority. So, but total processes which are estimated or created are P1, P2, P3 and P4. But P4 has not yet resumed, right? And it is not listed in the ready queue because these are the three ones which are created at the first, and then later after some time it is created and it enter into ready queue. So then among these P1, P2, P3, the shortest one is, as we have adopted the shortest job first, the shortest job or what you call it in a process is 5 millisecond. This is the P2, just where I'm showing, I'm moving the cursor, making the circle on the slide. P2, it takes 5 millisecond. So that's why the P2 will be given chance. Look at here. Before P2 required 5 millisecond to completely execute its code, but before it finishes off, P4 is will resume and it enter into ready queue. When the P2 has finished 2 millisecond of its execution out of 5, look at here where I am pointing, out of 5 it has finished only 2. Before it finish, the P2 with the 2 millisecond enters into ready queue. After that, the P2 has to give up the CPU time to scheduler will check once again the ready queue list where the P4 has entered with shortest, right, time estimated. So that's why in the previous list P1, P2, P3 were where out of 3 P2 was the shortest job, but or a process or a task. But when P4 enters into that queue, ready queue, the P4 is now the shortest job. That's why P2 loses its status of becoming a shortest job as soon as the P4 enters in that queue. So the P4 has to resume the execution. That's why the P2 is suspended, or then the P4 has to be given a chance. The P4 will, instead of P4, P2 is suppressed or suspended by the scheduler, and then P4 is picked and allotted the CPU time. And then the P4 will finish its execution for 2 milliseconds, and then when it finishes, the ready queue is again has only 3 processes in the list: P1, P2, P3. Again, the scheduler will check for the shortage of after P4 execution. It finds P2 again. Already P2 has executed 2 milliseconds. From that point, it starts executing, where the only 3 milliseconds remained. There it executes and give up the next shortest job. Next shortest job in the list of P1, P2, P3 is P3 of with 7 milliseconds. So that will be, this P3 will be picked to execute or scheduled the CPU time by a scheduler to execute its code. It finishes, and then last one is the P1. The P1 will be given a chance with the 10 milliseconds, and then it executes its complete code. So we'll try to calculate here the waiting period, how much the processes has to wait. So start with P2. So P2 has to wait 7 milliseconds to finish off its execution. So first, how much P2 has to wait? First, initially the P2 has started executing. That way, first initially it has 0 waiting period. That we noted 0 waiting period. And then the P2, when the in between the P4 resumes, and the CPU is allotted to it. That's why this P2, from P2 to P4, it has to wait, finish until the P4 finishes. P2 millisecond to P4 millisecond. Though 4 minus 2 means 2 millisecond it has to wait. Which one? P2 to finish its work. That's why plus 4 minus 2 will get a 2 millisecond waiting period. The P4 has to wait for 2 milliseconds because it has to not to wait for any, because as soon as it get into ready queue, immediately the CPU is allocated. That's why it takes a 0 millisecond, because this is the very shortest job in the list. Next, P3. P3 has to wait 7 milliseconds. Look at here, 0 to 7 milliseconds to start the execution to get the CPU time. So waiting for CPU, how much? 7 milliseconds. The P1 to start its execution, code execution, after CPU allocation. For CPU allocation by the scheduler, the P1 has to wait, look at here, from 0 to 14. How much? 14 millisecond time. So we'll add up all to get the average waiting period of all the processes is 5.75 millisecond. And the turnaround time in the sense, how much amount of time it takes to completely finish the process. For example, here P2 will take P2 will take how much time? So 7 millisecond. Actually it is a 5 millisecond is required for this, but in between the P4 will resume, come into ready state. Because of that, the P2 at that time, when P4 resumes into ready queue, at that time the P2 will become the which was previously shortest job, now becomes P4. That's why the P2 has to wait for another 2 extra millisecond. The total time which is required to finish its process is called the turnaround time. It's completely finished and goes into block state. That time is called the turnaround time. This is the 7 millisecond, and for P4 2 millisecond it is. And then turnaround time for P3, it is 14 millisecond. You can look at here, completely finish. And for P1 it is 24 millisecond. And the total average turnaround time of all the processes, we add up all and divide by 4, we'll get 11.74, as there are 4 processes. That's why we have divided by 4. So next scheduling algorithm, which one we can adopt, is round robin type. Round robin, all the processes are given equal time slot. All the processes are given equal time slot, right? And it's predefined. It is that execution starts with picking up the first process in ready queue, and it is executed for a predefined time slot, and then all the processes are given equal time slot, even though it may be the processes may have the different time for execution if it is required, even though it is allotted fixed, right, definite time slot, predefined it is all. Round robin scheduling is similar to that first come first served scheduling, and the only difference is that the time slice based preemption is added to the switch the execution between the process in the ready queue. So I told you that this is the ready queue, this is the ready queue. So for round robin it will pick first P1, then after 10 millisecond if it is the time slot allotted for every process, then look at here, the first it will pick P1, next will pick the P process 2, process 3, like that. So look at here, process 1 execution to process 2, process 3, process 4. So we'll try to understand with this simple example. So there are 3 processes with the process ID P1, P2 and P3, and the estimated time to complete its code execution is 6, 4 and 2 millisecond respectively, and the time slot allocated is at 2 millisecond. Look at here where I am pointing, round robin with the time slice 2 millisecond. In the ready queue it is P1, P2, P3 they have listed. So P1 will get the first chance, but the P1 need 6 millisecond to completely execute its code. In a first round it will get the 2 millisecond, but still as it is a 6 millisecond process, it need another 4 millisecond CPU time. That's why after 2 millisecond the P2 will be given a chance, and then the scheduler will pick after P1 P2, after P2 P3. Again P3 has only 2 millisecond and it completely finishes. Then again it will pick the P2, then P1 and then P2, sorry, P1 and then P2. After P3 P1, again P2. P2 already executed 2 millisecond and this 2 millisecond. Totally it finishes how much time is required allotted, and then P1 is picked, and P1 also finishes. So P1 and P2 at waiting period, P1, P2, P3's waiting period is different. How much P1 has to wait for CPU time? First 2 millisecond, 0 millisecond because it has started with the P1 only. Then P1 has to wait for this from first time slot to its a second time slot when it is allocated. Total 4 millisecond. So if 6 minus 2 will get 4. Look at here. And then P1 again second time and it allotted to third time allocation. The waiting period for this is 2 millisecond. Look at here, from this to this 10 minus 8. So yeah, you will get 2 millisecond waiting period. So P1 P2 first it has to wait for 2 millisecond because first P1 has started execution, and then from the 4 where we finished the first time slot to here allocation again second time when it resumes execution. So 8 minus 4 you will get 4 here. So total 6 millisecond it has to wait to finish its work. Waiting period for P3 is 4 millisecond. That's it. So total average waiting time is, you add all this and divide by 3 as 3 tasks are in queue, ready queue. And turnaround time is for P1 it is, turnaround time means the amount of time taken to completely finish its execution. For P1 it is 12 millisecond, and for P2 it is, let's look at it, 10, and then for P3 it is 6. So we'll add up all and divide by 3. We'll get 9.33 as a millisecond. This is next, the priority based scheduling. So already I told preemptive priority based scheduling. Any high priority process enters the ready queue is immediately scheduled for execution. In a ready queue, if any higher priority immediately enters, immediately given scheduling for execution, and as soon as it enters into ready queue, already suppose priority 2, 3, 4 are in ready queue, and P1 has with the highest priority has not entered, and then when P1 list, as soon as they listed in ready queue, enters the ready queue, then immediately rest all the lower priority processes P2, P3, P4, if it is executing its code, it is suspended, and the CPU time is allotted to the higher priority process P1. The priority of the task in preemptive policy based scheduling is indicate that in the same way as that of the mechanism adopted for non-preemptive tasks. So here the process list queue is listed with the process ID, processes P1, P2 and P3, and the time slot is 10, 5 and 7 millisecond. The priorities of these P1, P2 and P3 are: P1 is 1, P2 is 3 priority, P3 is priority 2. Highest priority 0 and lowest priority 3 is the lowest priority time. And then P4 with 0 priority. 0 priority means highest priority. Enter later. Okay. So first in the ready queue are only 3. P1, P2 and P3. In a ready queue, so only 3 are listed first. P1 sorted the ready queue. P1, P2 and P3. And then P1 is the highest priority here. I told you 1 highest priority, 3 lowest priority. Look at P1 is the highest priority, then it is listed in this. So it has already, if it executes, P1 has 10 millisecond to finish, but before it finishes, the P1 executes only 5 milliseconds of it. P4 will resume listed. Estimated time slot it is required is 6 millisecond is listed in the ready queue. As soon as the P4 enters into the ready queue with the highest priority of 0, look at here, 6 millisecond process P4 enters into ready queue of a 6 millisecond with highest priority 0. Then rest all the priorities processor which are executing has to be suspended, and this has to be allocated the CPU time. So that's why here, look at here, P1 is suspended and P4 is allocated CPU time. It completely finishes all its 6 millisecond, and then it will give up the CPU time. Then in the ready queue, the processes are P1, P2, P3. In P1, P2, P3, again it will the scheduler will check for the priority. P1, it finds P1 as the highest priority among P1, P2, P3. After execution of the P4, it finds. Then it will pick the P1 and allocate the CPU time. And the P1 will finishes its completely execution code. And then in a ready queue, P2 and P3 are there. In the ready queue, it will scheduler will check. It will pick out of P2 and P3 the P3 because look at here, the priority, as I told already, priority P3 is 2 and priority the P2 is 3. The highest priority based preemption algorithm is used in the scheduler. That's why it will pick the P2 because P3 process, because priority of the P3 is 2 and priority of the P2 is 3. The highest priority is P3 process has P2, P3 is fixed and it finishes its execution. Then at the end, with the lowest priority, P2 process is given a chance to execute its code and it will finish its execution. So here in the previous slide we have explained how to calculate a waiting period time for each process, and then turnaround time each process is calculated. The waiting period for P1, first initially it is 0, it has started, the execution has started with P1, and then P1 has to wait from 5 to 11, 11 minus 5. P4 does not wait anything, so that's why it is 0. Then P3, so P3 has to wait, from 0 to 16 to get its turn. The same thing what is explained, 16, and the P2 has to wait, look at here, 0 to 23, and the average waiting period is sum of all these waiting periods and divided by 4, total 4 waiting, so let 11.25. Then turnaround time, the P1 turnaround time is completely finished at this 16th millisecond of the CPU execution, and then P4 turnaround time is 5 to 11, 5 minus 11, total 6 milliseconds, and then the turnaround time of the P3 is 23 millisecond. The question may arise why the P4 has done only 6 millisecond turnaround time, because the at the beginning only 3 processes are listed in ready queue and P4 will resume after 5 milliseconds. That's why the turnaround time of the P4 is 6 milliseconds only. Right? That's why we calculated the turnaround time The moment it resumes, it listed in ready queue. From that point, we have to take the turnaround time, the time required to completely finish. That's why it has resumed at this time slot, time period, and then it has resumed till 11. That's why it's called 11 minus 5. Then if you add up and divide by 4 to calculate the total average turnaround time. Okay. Thank you for watching the video. If you have any doubt, please send me the mail. I will clear the doubts. And please subscribe for further updates.